Hey guys, this looks like a fun one. We're given 4 squares, and this one has an area of 2, and it wants us to find the area of the green square. This is day 16 of the 2025 Advent calendar. It's my goal to solve all these by the end of March 2026. And if you want to try this one, pause it right now, because I'm going to solve it in 3, 2, 1. First, I want to focus on this blue square. The area of this is equal to 2. What is the diagonal equal to? First, we can find the side lengths. If the area is 2, these two sides will be root 2. And that's always true. If you know the area, you can just square root it to get the two sides. And to verify it, square root of 2 times square root of 2 is equal to square root of 4, which is equal to 2. And then to find the diagonal of a square, you always do the square root of 2 times the side length. Here are the notes for that right here. So now in the place of the side, we can plug in square root of 2. Square root of 2 times square root of 2 is equal to square root of 4, and that's equal to 2. So the diagonal is also equal to 2. For this square, the area and the diagonal are numerically the same. Technically, the diagonal would just be in units, but I still think it's kind of a cool property. Let's put a box around it. This box is huge. Very nice. This is much better. So in every square with the area 2, the diagonal is also equal to 2. Now that that's out of the way, we can focus on this problem. Since this goes through these two vertices, this is cutting the angle in half. This would be a 45-degree angle. That means that this side of the yellow square is part of the diagonal of the large blue square. Because in the blue square, this would also be 45 degrees. And then we can also mark this angle as 45 degrees. Once again, because this is the diagonal of this square. I'm noticing along the sides of this angle, we have some intersections of some of our squares. Let's mark the intersections. The green square and the yellow square intersect here. The green square and the large blue square intersect here. And the little blue square and the large blue square intersect here. Now that we have 3 points, we can construct the unique circle that goes through those 3 points. Here it is right here. And you can do that for any 3 non-collinear points. Any 3 points that don't lie on the same line have one unique circle that goes through them. Let's go into Desmos really quick. I can show you. So for these 3 points, here's the unique circle. And as you move the points around, no matter where you put the 3 points, there's one unique circle that'll go through them. And then if you line up the points in a straight line, the circle vanishes. It's impossible to draw a circle through 3 collinear points. That's 3 points that lie on the same line. And this is the unique circle through these 3 points. So now from here, if we mark the intersection of the little blue square and the green square, that's right here, that looks like it could be the center of the circle. And to support that, if we draw this line and this line, these 2 lines are going to be equal to each other. So these possibly could be radii of the circle, but we don't know for sure. Just because a point is equidistant from 2 points on a circle, it's not enough to prove it's the center. For example, we can choose a point right here. This can also be equidistant from these 2 points, but is clearly not the center of the circle. So these 2 being congruent is not enough to say that this is the center of the circle. We got to see if we can find some more evidence to prove it. And to do that, for the next step, let's focus on this angle. This 45 degrees is for sure an inscribed angle. We know the vertex of the angle is on the circle because we defined it that way. Let's look at this arc that is subtended by the angle. In a circle, the measure of the arc is twice the measure of the inscribed angle. Here's some notes right here. So this purple arc is going to have a measure of 90 degrees. And now we can go back to here. This angle is one of the interior angles of the green square, so we know it's a right angle. And in a circle, the central angle is equal to the arc measure. Now we have enough to know that this is the center of the circle. Since this point is equidistant from these 2 points and the central angle matches the subtended arc, that is enough to know that this is the center of the circle. Let's color it red to match the circle. Now that we know this is the center of the circle, these 2 congruent sides are going to be equal to r for radius. And then we can clean things up a little bit, and let's draw the radius from here to here. And we can label it r. And now this is my favorite part. This radius is the diagonal of the little blue square. We showed earlier that the diagonal of the little blue square was equal to 2. So the radius of this circle is equal to 2. And that means these 2 radii will also equal 2. And now we can find the area of this green square. Since the base and the height of this square are both equal to 2, the area of the square is going to be equal to 2 times 2. And that'll be equal to 4. We can give it a label of square units and put a box around it. And that is the answer to our question. In this given problem, the area of this green square is equal to 4 square units. How exciting. And this is the next question. We're given 3 squares inside of a circle, and it wants to know what is the area of the circle. This looks like it could be a fun one. How exciting.